Okay, today we're looking at what are called related rate problems. Related rate problems look at two variables that change with time and are related to one another. All right, so let's look at what we mean by this. Okay. Let's say y is a variable, and then dy dt is the rate at which it changes. So if y changes with respect to time, then dy dt is the rate at which it changes. So let me just emphasize that here we're assuming that variable y changes with time. So here we have a concrete example. It says, suppose that y is equal to 6t plus 1 over t squared is a function that describes the distance in miles of a marathon runner when t is hours. And let's assume that t is equal to 1 to 4. So that means at hour 1, you can substitute in the distance, and after hour 1, the runner has run 6 plus 1, or 7 miles. Let's look at dy dt. We're simply going to differentiate this function. Dy dt is 6. The derivative of 6t is 6. And the derivative of 1 over t squared, we'll write this as 1 over t squared. That's the same as t to the minus 2. So when we differentiate that, we bring down the minus 2. So we have minus 2 t to the minus 3, subtracting 1 from that exponent. So this is dy dt, and it describes the rate of the runner in miles per hour. All right, so for example, here, if we want to know, well, let's say we want to know how many miles has y covered when t equals 2. How many miles? Well, that would be y. Y is measuring the distance, the miles. Okay, so that would be 6 times 2 plus 1 over 4, 12 and a quarter miles. All right, and what is the rate at which the runner is running? What is the rate at, let's say, t equal 2? So then we go to the derivative and we say, let me just scroll up a little bit here, dy dt when t is equal to 2 is 6 minus 2 times 2 to the minus 3. 6 minus 2 to the minus 3 is 1 over 2 cubed, or 1/8. So 6 minus 2 times 1/8. 2 times 1/8, that's 1/4. 6 minus 1/4, or 5 3/4 miles per hour. Okay, so that's how, that's the rate, or how quickly the runner is running when t is equal to 2. In related rate problems, we usually have more than one variable. Okay, we have a situation like this. We have at least two variables that are changing with time. In the above example, we only had y. Y was changing with time. The distance that the runner ran was changing, kept increasing as t increased. Here we have two variables, x and y, and they're both changing with time, and x and y are related. Okay, so x and y are related and both change with time, and the question is, how are their rates related? Okay, so this means, how are their rates related? Very often we're asking, how are dx dt and dy dt related? Those are the rates. So when we say rates, we mean dx dt or dy dt, or some derivative with respect to t. Okay. So here's an example, just sort of building on the previous example. This time we have two friends, x and y, are running in the marathon. Okay, so x is equal to 6t plus 1 over t squared, the same function we have up here. And that describes the distance in miles that x runs, where t is given in hours. And suppose that y is equal to 3/4 x. So what does that mean? That the distance that y covers is 3/4 the distance that x covers. So y is running a little bit slower. Okay, that is, y covers 3/4 the distance that x covers at any given time. How are the rates of x and y related? Well, the rate of x, we know it's right here. Okay, we can just differentiate that like we did above. But we're asking how are their rates related, and we want to know when t equals 2, find the rates at which x and y are running. Okay, so let's look at this. It's pretty simple to find how the rates of x and y are related. Right, what we do is we see how x and y are related. This is how x and y are related. And to find how dy dt and dx dt are related, what we're going to do is we're going to differentiate both sides with respect to t, variable t or time, even though t does not appear in this equation. So on the left side we have dy dt, it's very simple really, and on the right side we have 3/4 times dx dt. So that answers the first part, how are the rates of x and y related? This is how the rates are related. And again, we got it, but just by differentiating the equation that tells us how x and y are related, just differentiating this with respect to t. Let's answer the second part. It says when t equals 2, find the rates at which x and y are running. All right, so let's do that. Let me just do it here. When t is equal to 2, well, first of all, dx dt is equal to that. Here's x, and we know what dx dt is, just we differentiated that already, and we got 6 minus 2 over t cubed. That we did already. Okay, so just substitute in t equal 2. So this is equal to 6 minus 2 over 8. This we also did in the first problem, in the first example. 6 minus 1/4, so that's 5 3/4 miles per hour. Okay, so that's how fast x is running when t equals 2. And what about y? Well, y is 3/4 of dx dt. Sorry, dy dt is 3/4 dx dt, so all we have to do is say, well, when t equals 2, we know what dx dt is. Dy dt, we just figured that out, is 3/4 times, this is dx dt when t is equal to 2. Okay, so we do that, so that's 3/4 times, I'm just going to change this to a fraction. This is 23 over 4, and so we have, just multiply the fractions, 16 in the denominator, and in the numerator we have 69 over 16 miles per hour. That's the units. So that answers this second part of the question. Okay, let's continue with these types of examples. So picking up where we left off before, suppose now that we have 3 friends that are running. So before we looked at 2 friends, let's go over this again. We had 2 friends that are running. We knew the 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 relationship between x and t. Okay, so we had that equation, the distance function for runner x, and then we said that x and y are related by this equation. Y is equal to 3/4 of x. So we could, using this equation we found dx dt. Using this equation we found that dy dt was 3/4 of dx dt, so we could find dy dt as well. Okay. Now here we have a situation where we have 3 friends, x, y, and z. Now we have the distance function for x, so we can figure out dx dt at any value of t. And here we're assuming that y is equal to 1/2 x plus 1/4 z. In other words, the distance that y covers is equal to half the distance that x covers plus 1/4 of the distance that z covers. And we're also told that z is equal to 5/4 x. So the question is, when t is equal to 2, find the rates at which x and y are running. Just x and y. We're not really interested in z, just x and y. All right, now let's say when t equals 2, find the rate at which x is running. That's no problem. We can just calculate dx dt over here and substitute in t equal 2. So that one's no problem. How about y? Well, if we differentiate this equation, we end up with dx dt, and then on this side we'll end up with, dy dt over here, and here we'll end up with the dx dt, and here we'll end up with dz dt. So I won't be able to get dy dt because I know what dx dt is, that I can figure out, but dz dt I don't know. So what we're going to do here is typical for what we do for a lot of related rate problems. First, we're going to get rid of the variable that we aren't interested in. We're going to get rid of z. We have this relationship here that will allow us to write z in terms of x. So we're first going to substitute. So in other words, here, let me just circle this. This is what z is equal to. We're going to put that right here instead of z. And so then we'll have y equal to some equation with only x in it. And we can proceed like we did in the above example. All right, so let's do that now. So we'll start by figuring out dx dt. We know that we did that already in the previous 2 examples, and we saw it was 6 minus 2 over t cubed. Okay, so now we can figure out when t equals 2, we can figure out what dx dt is. So this says when t equals 2, find the rate at which x is running. Okay, so we have to find dx dt when t equals 2. All right, so in other words, just substitute in t equal 2. So dx dt is equal to 6 minus this we did 2/8, 6 minus 1/4. That's 5 3/4. That's that rate, or as an improper fraction, that would be 23 over 4. All right, so we have that value. So we have the first part. Now we want to figure out dy dt. So next what we're going to do is we have y equals 1/2 x plus 1/4 z, and we have z is equal to 5/4 x. So we're going to first substitute and then differentiate, which is usually how we do it. Substitute, get rid of a variable, the unwanted variable. So this is common in these related rate problems. First sub, then differentiate with respect to t. I'll just write it like that. Then you find dy dt on this side, and on the other side it'll be dx dt. Okay, so let's do the substituting. Y is equal to 1/2 x plus 1/4, and now instead of z we're going to write 5/4 x. Okay, so what's that equal to? That's 1/2 x plus 5 over 16 x. So just add and change 1/2. 1/2 is equal to 8 over 16. So we're adding 8 over 16 plus 5 over 16, so we have 13 over 16 x. So let me rewrite this. We have a simple equation, y is equal to 13 over 16 x. So that means now we can differentiate dy dt equals 13 over 16 dx dt. And so when t equals 2, we want to figure out what is dy dt when t equals 2. So let's do that. When t equals 2, dy dt is equal to 13 over 16 times the result that we got over here. Let's see. Let's go back. Where is that? The result that we got here. This one. This is dx dt when t equals 2. So we're going to just put that 23 over 4 right here. Okay, so the numbers don't work out to be that nice, but that doesn't really matter. So just multiply the numerators over here, and we have 13 times 23, that's 299, and 16 times 4, that's 64, and that would be a rate in miles per hour. So we answered the two questions. We found dx dt when t is equal to 2 up here, just substituting into this derivative. And then to get dy dt, well, we relied on this equation, getting rid of the z, and we were able to find what dy dt is since we already had figured out dx dt. Okay. So those are our two answers to this problem.